This section is about Bayes' theorem. So for example, it's estimated that 0.6% of the American population has the HIV virus. So as you do any problem in this class, start by writing down what they tell you. So probability of HIV equals 0.6%. Let's change that to a decimal, so this would actually be 0.006. A diagnostic test is used to attempt to detect whether a person has HIV. According to historical data, 99.9% of people with HIV receive a positive test result. So the probability of getting a positive if you have HIV, notice it did say of people with HIV, is 0.999. We also know that overall people get a positive test result 1.6 of the time. Notice this is just overall positive. It didn't say anything about whether or not you actually have HIV. Probability positive is 0.016. So write down all the information with symbols. Okay, we did that. What's the probability that an American has the HIV virus and they get a positive test result? Okay, so it's asking for the probability of HIV and positive. Okay, that's not one of the things we saw up above. So if you want to find the probability of an and, we have to use the general multiplication rule. So find any conditional probability you have. So let's do probability of positive given HIV. Now you have to make sure you multiply it by the right one. So given HIV means that we have to multiply it by probability of HIV, because you always multiply by the second part here. So this will be 0.999 times 0.006, which should give me 0.005994. Now, of course, the test isn't perfect, so people with HIV sometimes test positive, and 1 in 100 people without HIV get a positive test result. We would like to know the probability the person has HIV if they get a positive test result. So that means now we're saying that we know they got a positive, and we're looking for the probability that they have HIV. So use your formula, probability of the intersection, or the and, divided by the probability of what comes second, so probability of positive. So the and we had to find up above, so 0.005994 divided by probability of positive, 0.016, gives me 0.3746. So that means for this specific test, if you get a positive test result, there is only a 37.46% chance you actually have HIV, which seems kind of low. Sometimes this happens with diagnostic tests, and it's interesting to look at this kind of reverse conditional probability. So up here, the probability that you get a positive if you have HIV was really high, but the probability that you got a test result and you actually have HIV, which is what you'd be more interested in, is quite a bit lower. Now here's where the Bayes' theorem actually comes in. So notice we start with the probability of positive given an HIV, and in steps B through C, we found the probability of HIV given positive. So we switched the order of our conditional probability. We can combine those steps to see the probability of HIV given positive equals the probability of positive given HIV times the probability of HIV over probability of positive. And because that's what we did in the two different steps, you can stick it together and do it all in one step. So Reverend Thomas Bayes discovered the shortcut formula. It's useful when we know one conditional probability, but we're interested in the reverse conditional probability. So here it is, probability of A given B equals probability of B given A times probability of A over probability of B. You can use this every time you want to switch those, or you could just do it in multiple steps like we did. And let's do one example with this. So again, we have our Jim and Mary situation. So we had the probability of Jim equals 0.6, the probability of Mary equals 0.5, and the probability of Jim given Mary equals 0.8. So now let's find the probability that Mary watches TV if we know that Jim does. So we found this before in 2 steps. Now let's try and do it with 1 step. So the formula says, let's scroll up so we can see both at the same time. Let's see, so this is Mary, Jim. So A is Mary, B is Jim. So we should have the probability of Jim given Mary times probability of Mary over the probability of Jim. So we have 0.8 times 0.5 over 0.6, which gives me 0.666.